Thank you, Roger. And thank you, Ravinder, for the opportunity to come talk here. So as Roger said, my name's Drew Chambers. My role is I'm the business director for photolithography at DuPont. And I already confessed to this, but I am a chemical engineer. And so first question is, well, why is a chemical engineer at an electronics conference, right? IEEE event especially, okay? You EEs are special. We put you on the other side of the building. So, but yeah, grew up as a chemical engineer. Now I'm on the business side. So what am I doing here? Well, a little bit of my background. I had the opportunity when I used to work in a different part of materials. I did a lot with automotive sensors. So I did a lot of work with pressure sensors, oxygen sensors for cars on the materials side. But then for my semiconductor background, I really started to appreciate the fact that it's not just the sensor that was actually touching the powertrain. It was actually the control module that actually made the car fuel efficient, that made it more energy efficient, less emissions. So how those two things connected are really important when it comes to sensors. And today, what I'll spend a lot of time on is when we look at sensors in an overall setting, how do we actually connect all this data we're collecting from sensors and apply it into systems with networks, AI, machine learning, so we get the most out of all these new data inputs. I saw something online that sensors, I believe, Bruce, you said like there's 3 trillion sensors or something crazy like that. Well, what I read online is it's still continuing to grow at 8 to 10% per year, at least through 2035. So now you're talking about an incredible amount of data that's going to be generated. The question is, what do you do with all this data? How do you get it from the sensor itself to a network to an AI module that can actually do something with that input? So that's a lot of what I'll spend on today and the challenges of getting the chips to the point where they can actually do these things. Before I get there, I wanted to talk a little bit about the company I work for, DuPont. Now, DuPont is a materials company. I'm in the electronics space of that, but they also do quite a bit of work in water protection, industrial, things like aerospace and medical, and then also next generation auto. So we're in quite a bit of different areas. But I also wanted to talk about how big the company is. It's very diverse. We work in 50 different countries, and I have 24,000 coworkers. So it's a very big company, but the electronics part is actually about to go through a very exciting change. The electronics part of the business is about to spin off into a standalone company called Qnity Electronics. At Qnity, it'll be one of the larger pure play material suppliers in electronics going forward. We're planning on launching in November 1st, 2025. Qnity is going to be focused on a lot of the giant electronics megatrends. We're talking about AI, automation, power management, high speed, high frequency, thermal management. Not only areas that we're playing in as a company, but also if you think about sensors, a lot of these issues directly or indirectly touch the sensors. So let's talk a little bit about technology. I really like this qualitative chart because it talks about how technology has grown over time. One of the key takeaways when I first time I saw this was how much faster the technology cycles are closing and how much more technology is advancing. As we enter the 6th wave, what we're really starting to see is AI, sustainability, IoT, and automation are all becoming much more critical this technology phase, all include sensors. Now let's talk about it quantitatively. The growth in connected devices has been growing significantly, and it's been taking off at a double-digit rate recently. Everything's getting connected. From the consumer standpoint, what's being experienced is more email, more phone calls, more content being uploaded. People love their cat videos. Underlying growth drivers of this is 5G, data centers, EVs. All these things are driving the need. But let's talk about where sensors fit into this. Sensors are everywhere. They're really going to be the eyes and the ears of AI. You have sensors in a lot of different applications. Pretty much everything consumers touch and industrial touches is going to be hit with a sensor. Now back to the question I said is how do you take all that good data and turn it into something usable? A sensor without a place to put the data can only take you so far. an AI system that has no good data inputs is a useless model. The relationship between sensors and AI is symbiotic, but that also includes making sure you have the networks to connect and collect all this data and collate it so it can be used quickly and easily to generate good decisions. So, from an industry standpoint on the semi side, they're acting now. You have to realize that for every new megatrend that's coming, the semiconductor industry has to be thinking 4 to 5 years in the future to build the assets needed to manufacture those chips. A lot of what we're talking about today, and probably has been published, is how sensors and software are being generated. The challenge is for semiconductor manufacturing, how do they keep up? Because it's not just the intellectual capital to develop new software, develop new models. It's about putting physical assets together and then putting a manufacturing process to create these chips. The industry is investing significantly. In 2028, in 1 year alone, there'll be $188 billion of investment in manufacturing. That's a lot of capacity. But the reality is, at the same time, the right-hand chart showing you how many more wafers are needed to generate all those chips. A 9% growth per year is pretty significant to get all those chips manufactured, to generate all the modules that'll be needed to create AI, networks, and all the other things we do like IoT. So, let's get to the real hard stuff, which is what are customers telling us to get there? They're giving us tougher technical challenges. They want sustainable solutions, and they want it all done faster. So I'll talk about how we're going to get there after we talk about what the challenges are. To really appreciate this, I don't know if many people in this room understand this, but the semiconductor manufacturing process only is a few different steps. I know, Paul, you're going to say I'm crazy for calling it a few simple steps, but the reality is it's a few simple steps done a couple hundred times. Simple chip, and I'm going to have Paul correct me here, maybe a simple chip, 400 steps. More complex chips are getting over 1,000 steps now. So the thing is, you have to realize you're starting with a blank wafer, and then you're going through all these different manufacturing steps in an iterative process. They're all interconnected. So if you want to make one change to one module here, it impacts both upstream and downstream. So there's an incredible amount of R&D and engineering put in to make even simple changes to a manufacturing process. Otherwise, you lose throughput and you lose yield. Even when you look at the fact that you get the packaging and assembly after the chip is done, it's incredibly complex to shrink down to the die and the form factors people are looking for now before you can put it in the final product. So these innovations we're talking about are driven, I think we talked a little bit earlier at the panel, collaboration with the customer. They're giving us direct feedback of what they need to enable these next generation chips. And I'll show you some of the history of how we got where we are today. This technology roadmap talks about, for logic chips, how the gates have shrunk over time. And for perspective, when you think about gate width, which is now measured in nanometers getting down to angstroms, the smaller the gate, the faster the processor. The smaller the gate, the tougher it is to manufacture it. At 90 nanometer, we're talking about a strained silicon gate, which had one material challenge. We're now talking about, at 2 nanometer, a gate all-around structure that has much different materials, much tighter requirements for photolithography, etch, and clean. On the packaging side, we went from just putting a straight chip on a printed circuit board. Now you're talking about system and packaging, going all the way up to heterogeneous to get to both the form factor and processing speed customers are looking for. This is really challenging because they're asking us for lower power consumption, the performance I talked about. They need a very small area to fit into a lot of the devices we're talking about, and they all want it at a certain cost price point. If it's too expensive, no one can afford it. From a lithography side, when we talk about those gates, it's gone through an incredible revolution in the last few years. To print a gate, you typically do an image and then etch. But to get smaller gates, you had to do multiple prints called litho, etch, litho, etch. And as you can see over time, going from left to right, we added more litho etch steps The challenge there was not that the litho cost more, but you added a lot more manufacturing steps, which drove up cost and reduced cycle time. This led to what we call EUV, or extreme ultraviolet wavelengths. For perspective, the prior immersion technology on the left was 193 nanometer wavelength. We're now at 13.5 nanometer wavelength of light. Incredibly technically challenging to get that to work. Just to give some appreciation for what had to happen, immersion lithography 193 used a laser, there's an argon fluoride laser. That was tough at the time. EUV, to get a 13.5 nanometer wavelength, you're taking a drop of tin, firing a laser at it, and then hoping the wavelength comes off. And you're doing this over and over again in cycles, measured in cycles per second. It's incredibly challenging, and that leads to some of the costs we see here. But it has incredible technical benefits to get the amount of chips and density of logic up. But it does cost significantly more, and as you can see, you're not getting away from the layer litho etch pattern, you're actually getting into it very quickly. This is what's leading to the next challenge, which is high NA EUV, which is giving you that better patterning. The challenge there is the tools have gone from $50 million to $150 million to now $300 to $400 million per tool. So what engineers are having to do in these fabs with this kind of investment is figure out how to get high yield, high throughput very quickly. Otherwise, the return on these kind of developments isn't going to be there. Now, let's talk about the challenges with high NA EUV. When you have a wavelength of light at 13.5 nanometers, it absorbs on every surface. So the amount of photons available to actually pattern the wafer are incredibly small. Right now, the industry is using what's called chemically amplified resist, and it works quite well, but as people are looking to do finer patterns and get higher throughput, it's requiring people to look at many different ways of doing this, including chain scission, metal oxide resist, multi-trigger, or even dry resist. All these are being looked at as ways to create and enable the next gen chips. Etch also has its own challenges. When you look at some of these very complex gates like FinFET and gate-all-around, you're actually having to etch at the angstrom level with materials that are very close to each other. Being able to clean up silicon versus silicon germanium to create that gate is incredibly challenging and requires a lot of R&D. The other aspect is memory. 3D NAND is how we're storing all our information right now. The thicker the 3D NAND, the deeper the trenches, the tougher it is to clean them out. This is leading to another challenge. I know it may not be what everybody's interested in, but there actually is a conference next week called the Surface Preparation and Cleans Conference, where a lot of these technologies will be presented for the semiconductor side. CMP, this is another area where essentially you're chemically, mechanically planarizing the wafer. The wafer needs to be flat after every process step. But as it's going forward into the technology, the demands are getting more rigorous. Defects are becoming very challenging. Every defect on a chip results in a bad chip. Other aspect is layers are getting thinner. So when you have a surface roughness left over after polishing, it's transferring to the next layer, so you're causing performance issues. And topography, within die planarization, global planarization of these wafers has to be incredibly flat. When we talk about CMP, I need to give you a visual. If you imagine a wafer is the size of Texas, a bump on a wafer post-CMP is less than a basketball. It's incredibly flat. Now, the next thing that's coming in is new materials. We have ruthenium and molybdenum that are both coming in that enable next-gen devices. This is causing new R&D and new challenges because introducing new metals is incredibly challenging, and it's leading to a lot of new R&D that has to happen to be able to work on these devices with these new materials. Packaging doesn't get away. Packaging also has its own issues. As you're putting all these different components in a much smaller form factor, the thermal issues become incredible. So looking at how to get all that heat off the chips to keep the performance going is something that's incredibly challenging and being studied and researched quite a bit. So let's talk about sustainability. We get hit with all these technical challenges, but make it sustainable. Customers want both. When we listen to our customers, they give us some very clear things. They want us to act on the climate. They want us to do safe and sustainable by design, and they want to use lower waste. So these are the areas we're keying off of. The EU, from a global regulatory standpoint, is really leading in this area. But the interesting thing is all of you and all consumers in general are probably going to drive this before more than regulatory will. As people start to make decisions about what electronics they buy and what things they purchase based off the carbon footprint, how they're done, that will drive probably faster than the regulatory will. And that's something we're also paying attention to as a company. So when we talk about safe and sustainable by design, for DuPont, that means how do we deal with substances of concern? To do that requires three things we talk about. To get those new materials is going to require investment, innovation, and time. And we're spending all three right now to make sure we're dealing with these substances of concern. But in the meantime, we have to use all these substances of concern to make chips because chips are critical. So that leads us to really thinking about responsible manufacturing and making sure we're using these materials as we can. It also means looking at derogations so that our customers can use these materials responsibly to make those chips. The last thing we're really looking at is evidence-based policies to make sure that when we are making a substitution, we're not doing a regrettable substitution or finding unintended consequences based off the regulatory environment. So getting off of SOCs is really a balance. First, you have to plan to reduce or eliminate the SOC, but your new solution must be cost effective. That means affordability of your new solution, otherwise it won't be usable. The other thing we'll talk about is industrial competitiveness. Most of these materials, not just in semiconductor, but everything, are manufactured globally. That means the same regulatory environment has to exist in every region where this is used, otherwise you won't have parity or competitiveness. And then the final thing we'll talk about is performance and reliability. The new material we come out with must work as well or better than the current material, and the supply chain must be strong. It's not a good idea if you have a substitution, but if you can source it for high volume manufacturing, it won't be usable. So when we talk about regrettable substitution of these materials, it really falls into three categories: product performance, sustainability, and safety of the products to the environment and to people. So most people think about just the toxicology and the safety of the material, but that's only one aspect of it. When you're looking at a new material, you also have to think about the manufacturing process of that new chemical and make sure it's not having any adverse consequences compared to the material you're trying to replace. And then I already talked about it, but product performance. That becomes incredibly important in terms of making sure that you have high yielding processes for our customers. Otherwise, you have other unintended consequences. So IMEC is a consortia in Belgium, and with permission, they let me use this slide, but here's a great example of how a regrettable substitution can have an issue. The modeling they did shows that with a 1% die yield loss, you add essentially 20 tons of carbon per month. So as you're looking at these SOCs, you may be saving an SOC or dealing with a chemical issue, but the net negative of this is you just added 20 metric tons of carbon per month into the air. And that's something critical because of the energy usage. So this is just a good example of how a regrettable substitution could actually hit the environment. So let's talk about faster. How do we get there faster? That gets to a lot of what we talked about, or I touched on earlier, AI, machine learning. So how do you digitalize things? And this is the challenge we're going through at DuPont, but it has some very basic steps to it. First, it's connectivity. You have to take a lot of Cat5 cable and run it around your buildings, both in manufacturing and in the R&D labs. In some cases, you're trying to make tools that were never meant to talk to each other, get on a network. That takes a lot of work. That's why AI and machine learning doesn't just happen overnight. The next is how do you get all that data? Where do you put that data? And then more importantly, from a practical aspect, there's always inherent bias in the data that comes off tool to tool, and you need to make sure you're able to deal with that. So being able to scrub that data and be able to trust the data you're collecting is incredibly difficult, but something that's very important. Once you have that data, how do you integrate it so it's at engineers' fingertips? Once you've put it in a place that's easy to get, easy to access, and this is not trivial, by the way, it's then usable. And then you have good access for engineers, but then more importantly, you can take the next step into AI and machine learning. DuPont's already done some work here. In 2018, we brought machine learning in. In 2023, we did AI. And we've seen some improvement in a couple different areas, both technically and commercially. It's given us some real benefits that we've seen value in. But today, I'll talk about a couple of the technical examples we have of this. So in photolithography, PFAS is a commonly used material, and it has some very unique properties that allows it to help with the patterning of the wafers. But of course, PFAS, I think a lot of people have heard about, we need to replace it. At DuPont, we actually use computational chemistry. How do you build a molecule in a computer to understand how to do this? This saved us an incredible amount of bench time. We did a lot of modeling before we ever got to the bench because these syntheses are incredibly complex for these organic components. And it led to a very fast iteration of getting to a solution where we actually have comparable performance of a non-fluorine material compared to the PFAS POR. These are now being tested with our customers. Another example is on the clean side of things. We did some parallel work. We had a human do some DOEs. They can do about 100 a week. And we put it up against a model that could do 100,000 in a week. And that head-to-head test done in parallel led to some very interesting results. The human DOE took down the defect level 75%. The machine learning went down significantly more. So while the human got there, the AI model gave us a better solution. And that's been implemented with the customer, and the customer is very happy with this. So I know that's a lot different than probably what you were expecting to hear, or maybe what you're expecting at a sensor conference. But I did want to share this today to kind of show how the infrastructure is going to be put in place to use all the sensors we're talking about. So I hope you learned a little bit more about kind of the infrastructure that's going to be there. Likewise, I really have to say to the students who gave the posters today, I learned a lot more about sensors today. So I do really, really appreciate it. Hopefully you got something out of this talk like I got out of your posters. Thank you.